door, we have to push on the knob. If we have to open that door, we have to pull on that knob. Okay. When we are pulling a trolley bag in the airport lobby or on the railway station, we know we are actually applying something called force, right? Suppose my friend is coming towards me on a bicycle and I want to stop him. I know I have to push against his motion. I know it intuitively, right? So, yeah, we know when we apply. Yeah. And suppose I'm a batsman and I'm a batter and the ball is coming this way. If I hit the ball, I know I can change the direction of motion of this ball. If I don't touch it, this ball will go straight. Okay. Now, the force is not always causing an object to change its state of motion. For example, if I push on this wall, doesn't matter how much I push, this wall is not going to move. Okay, but still there is force. I am actually I'm attempting to push the wall. If there is a big train standing here, and if I want to push the train, I am not a Superman. I really cannot push the train, but this attempt is enough. Okay, there is some deformation. Now we can see the deformation very clearly. Now there is some deformation at the molecular level. If we closely look at our palms, yes, but we can see it very clearly if we take a rubber ball and if we squeeze it from both ends, we will see, oh, this ball is going nowhere, but the ball is the shape and size of the ball is changed. If we take a spring, okay, I don't have a spring here with me. If we take a spring, imagine this is a spring, and if I pull on the spring, the spring is getting stretched actually. The spring is getting stretched, like why would that is force. So just by looking at the effects, this is like an invisible spirit. This is like an invisible spirit. This is like an invisible entity. We cannot see it, smell it, feel it, but we can see the effect of this invisible entity. Okay, but very simply put, we say it is the push or the pull or the hit which cause an object to change its state of motion, or at least it tries to change the state of change of motion, or it changes or tries to changes the shape and size of an object. That is called force. That is how we intuitively understand that. Now, so far we are seeing, first of all, so we are surrounded by force. Okay, I am standing here. Apparently there is no push, pull. Is there any force on me? Watch carefully. Yes, my mass, my entire body weight is on the floor. And there is also a reaction force. Okay, you look at this picture. The weight is going in the downward direction towards the center of the earth, and then there is a reaction force. Okay, so that is contact force. So you are talking about contact. Most of you are saying that to experience force, when you are pulling this chair, we actually have to physically touch this chair. Imagine there is a string here. If I am pulling on this string, I am applying a force on this wall, okay, and I have to physically touch the rope to apply a force. And when I take this book, if I take this duster, and if I rub it here, yeah, there is frictional force. There is frictional force. I can feel it. Okay, I have to push it. There is a frictional force between this surface and this surface. Okay, they are contact force. But then there is non-contact force. Okay, and the common example of non-contact force is the force of gravitation between the earth and the sun. We know there is no physical media. There is no string, no rope connecting the earth and the sun, but there is a force which is holding them in their place. Okay, if we have, say, glass dot, if we rub that with silk cloth, electrons will be transferred, it will be positively charged, and then if we take it to small tiny clothes, pieces of paper, it will attract, non-contact force. Okay, and as a kid I am sure you all have played with bar magnet. Okay, if we have two bar magnets and like poles, north pole, oh, there is repulsion, there is north and south, non-contact force. So this magnetic force, electrical force, gravitational force, they don't need any physical contact of the objects. That is field force or non-contact force. Okay, now let's get back to this example when we are stretching the spring or squeezing the ball. They are not, their state of motion is not changed. Okay, and why? This is the balanced force. There are two forces. When the forces are acting on an object, if the forces are equal in magnitude but opposite in direction, they cancel the effect of each other. So we see spring, it is getting stretched. okay, but going nowhere. If I'm standing here, if Rick and Nick, suppose, imagine Rick is pushing me this 10 unit force, okay, and Rick is pushing me from the back side 10 unit force, and the effect of this 10 and 10 unit forces will be cancelled. I will not go anywhere. So this is balance. When there are more than one forces and they are equal in magnitude, opposite, and acting from the opposite direction on the same object, they will be called a balanced force. Like tug of war, right? Tug of war, two teams are playing. Yeah, no one is winning. They are balancing. They are balancing each other's counterbalancing. And what is unbalanced force? If the magnitude of the force is different, if Nick pushes me 20 Newton force this way and Rick is pushing me 10 Newton, yes, I will move in the forward direction. Alright, unbalanced force. This is easy to understand. See, the concept of force actually is so easy. We know all these things, but physics actually is giving us a systematic way to understand that. Okay, so any questions so far? No, good, that's good. So now let's come to Newton's first law of motion. It is saying, the statement is that, very simply put, Newton studied the motion of material object very carefully, and he came up with three laws that govern the motion of material object. This is like you watching a game for a long time and then telling the laws behind the game. Like if you watch cricket for a long time, you can tell the laws by which the game is governed. All right. So the first law is telling that an object at rest remains at rest forever, and it is saying that an object at rest remains at rest forever. Okay, and an object in motion remains in motion forever. Okay. So if the external unbalanced force is zero, that's the crucial point. So Newton's law, but can I feel it? Physics is about feelings. I mean, do I feel it? Yes, if the objects are at rest, I see the chair, table, desk, whatever, they are always at rest if I don't apply any external force. That is true. But what if I roll an object, it actually comes to rest eventually, right? Why? Because there is friction. If you imagine, let's imagine that you have taken a metal ball and you are rolling it over the carpeted corridor, it will go a certain distance. If you take the same ball and roll it over the cemented corridor, it will go a larger distance because the friction between the ball and the cement floor is less compared to the carpet and ball. Now if you imagine an extended Iceland, and if you throw that, what will happen? You will see that the ball will move even further. The friction is reduced. If you take that ball and throw it in space where there is no other distraction, no other force, what will happen? Yes, the ball will continue to move, right? So there is no friction. So that is the thing, that external unbalanced force must be zero. Okay. Now inertia. Now Newton's law is actually giving us a nice idea. It is basically giving us a concept that the natural tendency of an object is to remain in its own state of motion. If the object is at rest, it will like to be at rest forever. If the object is in motion, it will like to continue its motion forever. And this very tendency, this very property is called inertia. Okay? Inertia. When the object is at rest, it likes to be at rest. This is called inertia of rest. Let us get a practical example. Suppose you are sitting in a bus and reading a book, and the bus is at the bus depot, and suddenly the bus is starting. What will happen? You will bend like that. Why? Because your feet are attached with the floor of the bus. So as the bus is moving, your feet is going ahead, but the upper part of your body, they would like to be in the same place, and inertia of rest. Okay, you are not a rigid body. If you are like a solid iron made robot, yes, you will go along with the bus, but our body is flexible. Then inertia of motion. Okay, now the bus is moving on a highway, nice, there is no jerk, no bump at all, and you are reading once again a book, and the bus is suddenly braking because there is a herd of deer crossing the road. Okay, what will happen? Then your upper part will go in the forward direction. Why? Because the moment the bus is stopping, your foot and the lower part will immediately come to rest along with the bus, but your upper part, because of inertia of motion, would like to continue in the forward direction, and so you will bend in the forward direction. Okay, and inertia of direction. If you do not apply any force, okay, cricket bat, okay, if the ball is coming, if you touch it, yes, then it will go in that direction. If you don't touch it, it will continue in the same direction. If you imagine, like, if you have the cycle pedal, okay, the cycle pedal, If you imagine bicycle, you will see the wheels are, the mud is coming, rolling, and they will move tangentially. They will move tangentially. So if this is your wheel, if this is the bicycle, this is the bicycle, and so this is your mud going. This is your tangential. Okay? All right. Yeah, okay, thank you.